All right, you can, you folks can see me and you can hear me, right?
Yes.
Okay. So, what I want to do today, I want to finish off the unit, and I have some polling questions for you. That's what I was trying to set up as some of the polling questions. I don't want to start the new unit today. I think what I'll do is I'll start the new unit on Wednesday for you guys. So that way we have enough. I don't want to be too far ahead. Okay, so Wednesday I'll start chapter 29. Just give me a second. Okay, so before I get started, the homework is due tomorrow. I'm hoping that you've done everything except maybe the capacitor questions, or you probably could have done some of the capacitor questions already. Ohm's law is due on Friday. Exam 3 is on Friday, and then the following week, the DC Circuits lab is due. Okay. Does anybody have questions on the Ohm's law lab? Because I got a few over the weekend. No questions. Just to be clear, when you do part 2, this is your graph, delta V versus I. And I know it doesn't say delta V in the lab. I apologize. And then part 3, and you're just trying to find the equation that best fits your data. And again, don't do a 5th degree polynomial. Okay, it's hard to just interpret it. Okay, and I'm just trying to see how you interpret the graph. I just want you to see. I just want you to try to interpret it. Okay, that's all. I'm trying to get you to think. That's all I'm really trying to do. Because when it talks about the conclusions, all I want you to do is try to interpret this graph. And then in part 4, these are switched, and that's because the equation we use for, we have an equation for I as a function of the voltage across the diode. Remember, you're measuring the voltage across the diode, okay? Not the resistor in part 4. And also, and some people didn't catch this, when you do table 4, I think I mentioned it in lab 1 or 2 weeks ago. When you're doing table 4, it's going to be hard to do because our multimeters don't have a microamp scale. Okay, so it's possible you're going to have 1 sig fig on all your values. They might all be 0.00001. Okay, because of the fact we don't have a microamp scale. Because on a microamp scale, you would measure less than 1 microamp. Okay. So this is the only one where you're actually coming out with a value, because you're using this one. You're verifying Ohm's law, and so the slope of this graph, when you plot it this way, then the slope of this graph is the resistance. The software is going to give you the slope and the uncertainty, and then you can see that the range of values overlaps your measured value for the resistance. And then I sent you a new version of the lab because normally when I do this lab, I don't have enough time to talk about uncertainty of the meter. And so don't worry about the uncertainty in the meter in the Ohm's law lab. But then from the DC circuits lab on, we will worry about that. Okay? So no questions on this? Okay. I'll go on then. So we left off the other day, we finished off talking about RC circuits. And as a review, this has been since Wednesday, we discussed the circuit with a capacitor and a resistor, and I had a switch here in series. And we want to derive an equation for the capacitance as the charge in the capacitor as a function of time. And we derive the following. So Q is equal to Q max times, in parentheses, 1 minus e to the minus t over RC. So this was the equation we derived. This gives you the value of the charge in the capacitor as a function of time once you close a switch. And we derived it using Kirchhoff's voltage law. We said the sum of the voltage drops in the loop is 0. Okay, now we can define the time constant as R sub C, R times C. The time constant has, R and C have units of time. And we can write it like this. So you can ask, after an amount of time equal to one time constant, how much charge is on the capacitor? In other words, when t equals tau, so that this ratio is 1, how much charge is on here? And by the way, I forgot to mention Q max. The maximum charge you'll get in the capacitor when current stops flowing in the circuit is the capacitance value times the power supply voltage. And of course, when you graph this, graph looks like this. We can also get the voltage across the capacitor by dividing this charge equation by C. And that's going to give you the power supply voltage times 1 minus e to the minus t over RC. And I think I mentioned the other day that this equation is useful, really, if you need to know something in terms of time. Okay, I'm sorry, Sean. I missed your question. Sorry.
It's okay. We can come back to that.
Okay, I can hear you now.
Yeah, I had to do some adjusting.
Okay, let me finish my presentation.
Sure.
I'll come back to you. Okay. So this is the voltage across the capacitor, and if you take the power supply voltage, I'm using Kirchhoff's voltage law, minus delta V sub C, then that gives you delta V sub R, the voltage across the resistor. So if you do that, you'll get that equation. And if you divide this by the resistance, then it gives you the current. So what's another way to get the current? What's another way to figure out the current? Well, another way to figure this out is from Q, because we know I is dq over dt. If you take dq over dt, you'll get this expression. Okay? So these were the main equations we work with. And again, you really know that you really only need a time-dependent equation if you need to know q given t, or you need to figure out t given q. Okay? If you're given a value for t, then you can use these equations. But otherwise, I mean, you can use Kirchhoff's laws, for example, the voltage law, to figure some things out. Okay, just be aware of that. And by the way, when we look at if we look at this equation when t equals infinity, the q stops changing with time, the v start changing with time, and what you've done is reach the steady states of the system. Things are not changing anymore. Okay. Steady state means what happens when you let t go to infinity. Okay, so really when you look at, let's say this voltage has two parts to it. It has a steady state part, a constant part, and then this part has a transient part. Okay? The part that depends on time here is called a transient, the transient response of the circuit. And then this is the steady state part. Okay? So when I write that equation, this is called a transient, and this is the steady state. You're going to hear those, you'll hear those terms a lot. Okay, especially when you talk about circuits, not only circuits, but in other fields when you talk about heat transfer, etc. Okay? All right. So I'm going to do some examples today, and then I'm going to talk about the case when you discharge the capacitor. So let me go back to your question in the chat, Sean. So you couldn't get the fit to work. Did you define a curve fit, or?
I did, yeah.
And it didn't work.
It's in the same general shape of my data points, but the curve explodes towards a billion way faster than my data points do.
Okay. Let's see. You have the current in milliamps on the vertical axis, or amps?
I accounted for that in my formula.
Okay.
The first time I didn't, and it was really messed up, but I adjusted, and it's less messed up, but still not happy.
Can you email me?
Yeah.
Your your Cy-Davis graph?
Yeah.
And I'll play around with it. I'll look at it and see. Is there a weird data point on there?
No, it all seems pretty in line. I might have messed up a calculation or something. I'll send it.
Okay. And I'll take a look at it like after class, and then I can see. So once in a while you might have trouble doing a fit, but with Cy-Davis it usually works pretty well.
Yeah.
So, okay, I'll take a look at it. Okay, so I want to do a couple of examples. And I want to do something involving energy. First question you see in the slide there says, calculate the energy delivered by the battery in charging the capacitor. I want to know how much energy is delivered by the battery in charging this thing. Of course, once it's fully charged, I can calculate the charge in the capacitor. And we talked about this the other day, when we did chapter 26, that when this is fully charged, the energy it has is C delta V squared. And then the amount by which the amount that's delivered by the battery is twice this number. And I said that half of it goes through the resistor. Half is lost through the resistor. I stated that. I didn't prove it. Well, today I'm going to prove that. So I want to calculate the energy that's delivered by the battery. So how do we calculate the energy that's delivered by the battery? Well, power, I have so many equations here. Let me erase these equations. Power is voltage times current. And I want the energy delivered by the battery. And so I want the battery voltage, the power supply voltage, times the current. My equation for the current is that guy. And really, this is the rate at which energy is expended. Okay? This is the rate at which work is done. We want to look at the amount of work that's done by the battery. And so I got to find the work done by the battery. I got to integrate this thing. I want to integrate this. What's my limits of integration?
Do we go from 0 to t?
Yeah, but I want to know how much energy is delivered once it's fully charged. So what should my final t be? In theory, when is the capacitor fully charged? Well,
it's at infinity.
When it's an infinite amount of time it has passed. So I want to integrate this equation.
Should that r in your equation be squared as well?
Oh, I made a mistake.
Okay.
Thank you. Okay, so W and this is an easy integral, right? This is going to give me when I plug in infinity, what do I get? E to the minus infinity is 0, right?
Yep.
So aren't I just going to get this? That's the energy delivered by the battery. And this is the amount of charge on the capacitor. Okay. I mean, we know this from chapter 26. I don't have to derive it. But what about the energy lost by the resistor? So I already did part B already. The energy stored after it's fully charged is this. I mean, I don't have to derive it. How do we show that half the energy is lost by the resistor? Well, we look at the rate, we look at the rate at which energy is lost by the resistor. Okay, I'm just going to explicitly show this, that half the energy is lost by the resistor. When you charge a power supply with a battery. So again, you're going to look at the power dissipated by the resistor, and I'm going to write it differently. I'm going to write it as I squared times R. It doesn't matter how I write it, but it's normally when you talk about the energy lost by the resistor, you write it this way, I squared times R. And the equation for I, remember, was that. Oh, this is squared. Oh, and this is, I'm sorry, I wrote it wrong. Let me do it again, sorry. I screwed up. That's how it should look like. I squared times R. P dt then is going to be and so W is going to be the integral from 0 to infinity of this thing because this is squared, I got to put a 2 up in the numerator here. So I just got to integrate this. So let me go here. Now when I integrate this, again, this is an easy integral. And this term is 0. Oh, I forgot the exponential. This term is 0 at infinity, and so all I get so half the energy is lost by the resistor, okay? Half the energy delivered by the battery is lost by the resistor. So this is the total work done by the resistor lost by this, and then W to supply. And so the difference between the two is the energy stored by the capacitor. Questions? Okay. Let's look at the next circuit. Let me erase everything. Let's say I have the following circuit. I have a power supply. Capacitor. And I have a switch. Unfortunately, my two resistors are in bad spots, and I apologize for that. This resistor should be over here, but that's okay. So I have a switch S1 here, S2 here. Okay, so I close S1 and I charge the capacitor. I wait a long time. It's fully charged, and then I open S1 and close S2. What's going to happen? I've actually demonstrated this for you in the lab. Actually in the class, sorry.
The capacitor is going to discharge.
The capacitor will discharge. And I did that with the bulb. Remember when I did the demo with the bulb and the 1 farad capacitor? I also did it with the flash bulb and the 1 farad capacitor too. So the energy is going to discharge through this resistor. Actually, it's these two. I should have really put this over there. But so the capacitor is going to discharge. When this is fully charged, and then when it discharges, the electrons are going to go this way through the resistor. Okay, when it's discharging. So I want to find Q as a function of time in this case. Again, I have to apply Kirchhoff's voltage law. So how do I write the expression? Well, there's a voltage drop and a voltage. Oh, there's a voltage drop and a voltage gain. How am I going to deal with that? There's a voltage drop across the capacitor. But if the electrons are going this way, the current's going this way. If I sum the currents, if I sum the voltage drops this way, and this is a voltage gain, and that's a voltage drop, but I is dq over dt. Actually, I is not dq over dt. What is it? It's minus dq over dt. And so then I have q over c. And you separate variables. I'm not going to do the solution. It's in your notes. You separate variables. And you solve for Q. And when you do that, I get Q equals Q max e to the minus t over RC. And this is how the capacitor discharges. Okay, this is how the capacitor discharges. And so the voltage across the capacitor is going to be Q divided by C and I'm not writing this as the voltage across the battery because it really depends on where this is in the circuit. In this particular case, yeah, the delta V max is the power supply voltage, but it might not be in other cases. So I'm just putting delta V max there. And so in this particular case, Q max might not necessarily be the power supply voltage times C. So I'm just being a little bit more careful in how I write this. But like in this problem, it is. I mean, this is delta V sub S times C. And so this is the equation for the capacitor that's discharging. And of course, the current is going to be the derivative of this expression. And you'll get a minus sign in there because really I is minus dq dt in this particular case. So how much charge is on the capacitor after one full time constant? After one time constant, T, this ratio is 1. So I have, if you look at just Q over Q max, it's 37% of its initial value. E to the minus 1 is 0.37. Same thing with the current. If you look at the current after one time constant, you have 37% of your maximum value after one time constant. So I'm going to finish off this finish off the chapter with a fairly involved problem. And I think this is the kind of problem you should know how to solve. It's very easy to do the plug and chug problems with the Q's and stuff. Everybody should be able to do those. But you should also be able to analyze a circuit in different, what happens if t equals infinity? What happens if t equals 0? And so this problem I'm going to do in a second goes over that. However, before I do the problem, I want to demonstrate to you the RC circuit. So I have here, and I'm going to point the monitor down, and I'm going to get rid of that slide. I have here an RC circuit and a device to measure the voltage as a function of time across the capacitor. Now, if I use just a DC power supply, looking at voltage as a function of time is boring because once the capacitor is charged, it's charged and nothing interesting happens. And so I have a signal generator that basically turns the power on and off. And basically I'm putting in a square wave, a square pulse. I got to set this for a square pulse. Hold on a second. Okay, it's set to 1,000 hertz.
So it turns on and off 1,000 times a second?
Yeah.
Okay.
And then this device is called an oscilloscope. This is what you're going to learn how to use. On the lab on the 5th, I'm going to talk to you about the oscilloscope. And so this measures voltage as a function of time. So the vertical axis is voltage, the horizontal axis is time. And so let me show you the power supply voltage. This is the voltage coming out of the power supply. It's a square function. Basically, if you were doing this with a switch, you would be closing and opening the switch at a constant periodic rate, 1,000 times a second. Okay? So here I'm just turning, that's basically what this is doing. It's turning on and off the voltage 1,000 times a second. And this thing is able to monitor it. This knob here allows me to adjust the time scale on the horizontal axis. And then this here allows me to change the vertical axis, the scaling on the vertical axis. So like right now it says 1 volt per division. Okay. So the voltage coming out of the power supply goes up 2 volts above ground and then 2 volts below ground. And then the other channel, this is the voltage across the capacitor. And now I can see them both. Notice that the capacitor is not charging up to the maximum value. Why is that?
We're not giving it enough time.
That's right, we're not giving it enough time to charge. So if I change the RC time constant, if I make the time constant smaller, I made the time constant, how much did I make it? Oops, I messed up. Yeah, I made the time constant much smaller. Once I make it bigger, it won't charge up. So I went from I changed the capacitor from 1 microfarad to 100 nanofarad. So I divided the capacitance by a factor of 10 and made my time constant shorter by a factor of 10. So now the capacitor has more time to charge up, and you can see it reaches the maximum voltage. And again, if I make the capacitance bigger, you see the capacitor doesn't get enough time to charge up. Okay, the bigger I make the capacitance, the longer it's going to take for it to charge up. And since this thing is switching 1,000 times a second, I'm not giving it enough time to charge up. So let's do this. I'm going to change the frequency. I'm lowering it, and you notice that the capacitor is getting enough time to charge up. If I raise the frequency, if it turns on and off faster, the capacitor is not getting enough time to charge up. Okay, so you're actually looking at the charging and discharging equation at the same time on this picture. This is going to be, if you're an electrical engineer, this is going to be the most important instrument you'll learn how to use as an electrical engineer. It's much more useful than this guy, because this only allows you to see static signals. This allows you to see signals as a function of time. So this is going to be a very useful and important instrument for you. And so the last few labs you'll be doing this semester are going to involve you using this. So when we do the oscilloscope quiz, after that, all the circuits are going to involve you using this, and all the class, and they're going to be in person. Okay, because this thing costs hundreds of dollars. We can't include this in your lab kit. We were using smaller ones. They were like 20 bucks each, but they worked okay, just that the signal generator was very problematic. Okay, so this is much better, but this costs like 400 bucks. Okay, so anyway, we're going to have you guys come in person to do this lab. This is one of the labs you'll be doing. This is pretty much the setup. I have a resistor whose value I can change, a capacitor whose value I can change, and your signal generator. Question on this circuit? Okay, so you get to see at least what the RC circuit behaves like when I change things, when I change parameters, either the frequency, the capacitance, and of course if I change the resistance, you're going to get similar behavior. If I increase the resistance, then the RC time constant gets bigger and the capacitor doesn't have enough time to charge up. Okay. Let me fix the camera. So let's do this example. And I'm going to look at this, really in this problem, I'm just looking at the circuit, in extreme cases. Okay, I'm really going to look at this in extreme cases. You can solve this problem as a function of time. In fact, you folks actually have the math skills to be able to do it. But you have to solve systems of equations, and both equations are differential equations. You actually know how to do it. They're separable equations, so they're separate differential equations. So you actually have the skill to do this, but I'm not going to spend the time doing the problem, the intermediate problem. So let me draw my circuit. Probably not going to be very careful with this sig fig just because of space I have on the board, the lack of space. All right. So we're going to close the switch. And the first question says, when I close the switch, what's the current through each resistor? Notice how many times in this problem I use the time-dependent equation, okay? So I want to know what is I through each resistor when we close the switch. So I close the switch. Question is, how does the capacitor behave when I close the switch?
At that point, that's when we have maximum current to the capacitor, right?
Yeah, we have maximum current in our circuit. So how is the capacitor behaving then? In other words, so if I just have a simple RC circuit, and I put in t equals 0, my current then, is delta V sub S over R. So how is this behaving then? Because this is, the capacitor is not even in this equation at t equals 0. How is this thing behaving at t equals 0? is behaving like this, like it's a wire. At t equals 0, the capacitor acts like a wire. You get maximum current in your circuit. Okay? So that's the thing to remember, that at t equals 0, the capacitor is going to act like a wire. So then if that's the case here, then my circuit is going to look like this. And we all know how to solve that circuit, right? So we have these two in parallel. I say I gotta get a common denominator of 15. So our equivalent, 15 over 6 is 2.5. So really I had this circuit. And that reduces to so then my current through this resistor is going to be 9 over 14.5. And this comes out to 621. I'll use a different color. (621 microamps). And 9 divided by 14,500 gives you 621 microamps. So there's 621 microamps here. And there's 620 microamps here. What's the voltage drop across this thing? That's the voltage drop across it. So the voltage drop across these two remember that this replaces these two are in parallel, and so the current then is going to be this voltage divided by 15,000. And if you work that through, for both of these, this becomes 517 microamps, and this comes out to 104 microamps. That's at t equals 0, but then when time passes, of course, those numbers are all going to change. Questions on that?
Did you say it's 10.4 microamps?
104.
104, thank you.
Yeah. The sum of these two has to be equal to our 621. Those are t equals 0, right? Now, what if we wanted to know the charge on the capacitor as a function of time, or the current through each resistor as a function of time? What if we wanted to know that? Then what you would have to do is you would have to apply Kirchhoff's voltage law and current law, right? And there's two independent currents. This is going to be the sum of this current and that current. So you have two independent currents. You need two loops, and you solve the two loops, and then you can get Q as a function of time and I as a function of time. But it does require some work. One time I did go through and actually solved it. Okay, and the thing that makes this hard is this darn resistor. This resistor screws everything up. If this resistor wasn't there, you can write the equation for the current is a function of time, because if this wasn't there, the voltage across this resistor is the same. Because it's in parallel, it's directly in parallel to the power supply, and this whole thing is directly in parallel to the power supply. So you can easily write down the current, because the current here is the voltage divided by this resistance, if this wasn't there, and then this acts just like an RC circuit by itself, because it has 9 volts across it. So this messes everything up. Okay, that thing messes everything up. If that wasn't there, it's a very easy problem. But with it there, I have to use Kirchhoff's voltage law and current law, solve two loops, and they are differential equations. But you guys have the math background to be able to do it. Okay, and you can solve for I. And in fact, I did that. And if you want to play around with it, I looks like this. The current through the 3 kilo ohm resistor is this. And then through the 15 kilo ohm resistor, this might be a looks like that. I might have a round-off error here, because it doesn't match with this number, but I might have a round-off error, but that's what the equation looks like. So you can play around with it, and you can try to solve it if you want. Okay? But I'm not going to ask you to do it on the exam. That would take you a long time to solve it.
Thank you.
So what's the steady state current? What do I mean by that?
There would no longer be any current moving to or from the capacitor.
So that's an easy circuit, right?
A couple of resistors in series.
Yeah, that's all I have. So
Assuming S1 is closed, right?
yes. So this behaves like an open circuit, right? It behaves like there's something missing here. So basically I have two resistors in series, 27 kilo ohms. And so I then is going to be 9 divided by 27,000. $333 microamps. Have I used the Q as a function of time equation yet? Really not. Calculate Q max for the capacitor. What's the maximum charge on this thing? How do I know? How do I figure out the maximum charge?
We need to find the electric potential on either side.
I need the potential difference across this, correct? Since there is no charge flowing when the capacitor is charged, isn't it true that the potential difference between across the capacitor is the same as the potential difference between these two?
Yeah.
And then this potential difference is the same as this potential difference. Basically, I have this. This is my circuit. When you reach steady state, I basically have an open circuit here. It's as if nothing's there. And so whatever this voltage is going to be the same as the voltage across these 2 points, which is the voltage across the capacitor. So delta V of the capacitor is going to be 333 microamps times 15,000 ohms. And this comes out to be, I look it up here, 5 volts.
And that 3 kilo ohm resistor doesn't mess with those values at all?
Well, because there's no voltage drop across here, right?
Because there's no current.
Because there's no current, yeah. When there's current going through this resistor, yeah, then it messes things up. Because when there's no current, there's no voltage drop across this. There's no electric field. And so the charge in the capacitor is 10 microfarads times 5 volts = 50 microcoulombs. 50 times 10 to the minus 6 coulombs. Now, what is the current after I open the switch? Okay, so this thing is fully charged. So it's been like this for a long time. Then I open it. What's going to happen? Well, the capacitor is going to discharge through these 2 resistors. This 50 microcoulomb is going to go through these 2 resistors here. And it's almost like this part of the circuit isn't there. So what I'm going to have then is the following. with the capacitor discharging. Since the electrons are going this way, the current will be going this way. So what's the current? Well, this thing had 5 volts across it. When I close the switch.
So would we consider this as like a new time event where time equals 0?
I'm sorry?
Could we consider this a new time event where time equals 0? So
Yeah.
the whole exponential function goes to 1?
Yeah, you can set the clock again to t equals 0, right? So once you open that switch, then yeah, you can reset your clock. So how much current is here? Well, I have 5 volts divided by 18 kilo ohms. This comes out to 278 microamps if you do it on a calculator. 5 divided by 18,000. And that's going to be the maximum current, correct? And so the current is going to decay exponentially. So I is going to be the 278 microamps. If I wanted to, I could write it as a function of time. But what's this time constant? What's RT times C? Well, it's going to be 10 microfarads times this 18 kilo ohms. And so this is going to end up being, I'm running out of space. Let me know if you can see this. Can you see that?
Yes.
Okay. The last question is, I start with 50 microcoulombs. How much time has elapsed when I have 1/5 of this value, which is 10, but how much time has elapsed when Q equals 1/5 Q max? So when the capacitor discharges, this is the equation for a discharging capacitor. I want Q over Q max to be equal to 1/5. Obviously, I mean, Q will end up being 10 microcoulombs. I just got to solve for T. I take the natural log of both sides. And then I'm going to get rid of the minus sign by flipping this over using the rules of logs. So then T is RC times the natural log of 5. And if this is 0.18, this is going to give me 0.29 seconds. Yes, 0.29 seconds. So after 0.29 seconds, then the charge in the capacitor will be 1/5 of its original value. Questions on this? This is an important problem you should know how to solve, okay? Because it has everything, really has everything in this unit. Okay? Pretty much has everything in this unit. So make sure you understand how to solve this problem. Okay, so what I'm going to do, I have in the remaining time, because I don't want to start a new unit, I have some polling questions for you. So let me find some good questions for you. Okay, I'm going to try this one. I just have an assortment of them, so I can't do all of them. Okay. So, oops. Do you see the poll in the question?
Yes.
Okay. So go ahead and answer this one. There's 6 of you. You want to know which one's the brightest and which one's the dimmest? The practice exam has a great question on these kind of bulb questions. You'll have fun with it. Remember that I gave you guys the practice exam. I gave you a link to the old physics website, and I have all my practice exams there. So you would look at exam 2. If you look at practice exam 2 on the old website, that's going to be our exam 3. So. All right, so I got 3 people who've answered. We got 4. 2 more. I see. Okay, so everyone's responded. So I'm going to end the poll. I'm going to share the results. It's anonymous. So there's the results. Let me stop. I'm going to stop the share. So anybody want to explain their choice?
Yeah, there's a lot going on. I'm a little getting lost, but I think the brightness would be a function of current, and A is getting the full current of the circuit, so it should be the brightest.
Okay, that's correct. I mean, it has to be, right? It's getting all the
Yeah.
current.
And then as far as the other three bulbs are concerned, current is being shared between C and D, so they would be dimmer than B.
Correct. So then the choice would be, which one was
B.
it? B, yeah. Okay, good. Anybody have any questions on that? Okay, let me pick. Let's do this one. Okay, so okay, my computer's acting weird. All right, so I'm relaunching the poll. And here's a circuit. This is going to be a Kirchhoff's law question. This will take a little bit of time. I want to know which of those equations, if any, are correctly represent the application of the loop rule to the second loop on the right, the loop containing this power supply E2 and E3. So this will probably take a few minutes. And while you're doing that, while you're working on it, I'm going to draw the circuit on the board, and then we can talk about it. Okay, so I've got two people who've chosen a response. The one thing that this figure doesn't have, and one issue that this one has is that whoever drew this did not apply the current rule right away. Let's not worry about that. right, I got one more person. Okay, everybody. Okay, good. I'll share the results. And I want to ask one question. Why can I eliminate, let me see if I can eliminate any of the answers. Why can't I eliminate C?
The currents are drawn in the same direction, regardless of which way we traverse the loop. So their sign should be the same across the resistors.
What, and the power supplies?
Same deal.
Okay, so C should be out, right? Let's say I go clockwise. I'm going to sum currents clockwise. I mean, some voltage drops clockwise. So I'll start here. Actually, let me start here. I'm going to have a drop. If I go this way, I'm going to have, then the voltage is going to increase. Oops, I forgot to label some of these. This is going to increase. Then I go around and I get another drop. And then I get a gain. Does mine match any of those?
Kind of.
The signs are just switched, right? So they went in the counterclockwise direction instead of clockwise.
Okay, so yeah, so I chose, so if I went the other way, everything here would be multiplied by -1, right?
It feels icky to do that, but yeah.
I'm sorry, say that again.
It just feels gross to go that direction, but yeah,
Yeah.
It works.
And so that, which choice is that one then?
D.
So this one's D. So the answer was D. Okay, all right, great. Yeah, I guess that's all time I have. So on Wednesday, we'll start on chapter 29. Will be the new unit on magnetism. Personally, the third unit, especially when we get to the last chapter in the third unit, is probably to me the most interesting chapter in the whole course. Although we do have to treat it more conceptually because the problems tend to be hard to solve. But just the applications are kind of cool because we're going to look at, now that currents are moving, we're going to look at magnetic fields as produced by moving charge. And then we're going to look at time-dependent magnetic field and see what happens then. Okay. So I'm going to stop here. Before I go, do you guys have any questions?
Sorry. If you want to go ahead, Isaiah. Okay, sorry. Professor, you said, how long will you be at school today?
Well, I'll be here till 3. I'll be available till 3. I have a meeting between 3:30 and 5:30.
Yeah, 3. Okay, that's fine then. Because I'm planning on coming up because I still have a slight question on the lab as well. So.
Okay.
All right, so I guess I'll see you there.
Okay, and then Sean, just send me your data, your graph.
Isaiah, you can go if you want. Thank you, Professor.
Sure, no problem. Yeah, so
I'm curious if you're on campus at all tomorrow.
am I going to be? I will actually be here because I'm going to teach the class from here. Will I be available? Are you going to? Probably not. I mean, it's going to be. I have the same class tomorrow, but it's a 3-hour lecture. I mean, if you need to work in the lab, I can open up the lab.
I think it was going to be a homework questions. I just can't go in today.
Okay. Yeah, I'll try to get here early as I can tomorrow.
Yeah, no, I mean, I have lab. I have a chem lab from 10 to 2. So I was just curious if you were going to be on campus, but if not, it's totally fine.